Hello everybody. In this presentation, I will be talking about information and entropy. I'll be talking about the concept of information, how to measure information, what entropy actually is, and its mathematics. The reason I am doing this presentation is because what I always felt is that whether it is in books or whether it is in typical lectures, the mathematics behind the information and entropy is introduced immediately to a student. The underlying intuition is never explained. The fundamentals are never explained, and directly people are jumped onto mathematics of information and entropy. So I'm hoping that this lecture will be a bridge that will help explain these concepts first, help explain the intuition behind the mathematics first, and then comes the real mathematics. So that's what the intention of this lecture is. Now, moving on to the outline of this presentation, we shall be discussing the problem statement, basically the problem statement of how to measure information. We shall be deriving the information expression through intuition. So we'll be talking a lot about intuition. We'll be talking about some examples, and then we'll figure out how or what function is good measure for measuring information. Then we'll be discussing a couple of more examples in which we will actually find the value of information expression. And we'll use those examples to come up with a new concept, basically entropy. We will define the concept of entropy. We'll explain the concept of entropy through those examples. We'll also talk about how is entropy maximized, when can we maximize entropy, and then we'll conclude. So that's the overall outline of this presentation. So now to discuss about the problem definition a little further. The problem definition is that we need to define a metric to measure the amount of information that is conveyed by an event X. Okay. Now, what do I mean by that? See, somebody gets married, somebody has a child, somebody gets graduated, somebody gets a job somewhere, somebody moves to some other country or another state, somebody gets elected to parliament, a satellite gets launched into space. There's so many different kinds of events that can happen. How do you measure the information that is conveyed by each of those events? A tree could fall to the ground. A satellite could be following to the earth. How do you measure their information, and how do you compare them with each other? Are both of these events giving the same amount of information? So information is such an abstract quantity. It's very difficult to make sense of this quantity. And therefore, we have to define it. And if we have to define it, we must ignore or remove the subjective element of this definition. So we know that relevance of information is subjective. For example, a person's grandfather dies, right? That person definitely cares about his grandfather dying. His family cares. His friends probably care. But does somebody an unknown person, does that person care if this person's grandfather has died? No, unless the grandfather was a very famous person, a singer or a genius mathematician or a politician or somebody other than that. If somebody was famous, yes, more people care about their deaths, but for a very common person, I don't think that the rest of the world cares, because so many people die every day. So the point here that I'm trying to make is that the relevance of some amount of information is subjective. And being subjective, that cannot be an input to how we measure information. Information has to be the measuring of information has to be more objective. It has to be based on an objective criteria. And that criteria is the probability of that event. Okay. What is the probability that a tree would fall to the ground? What is the probability that a satellite will fall back to the earth? Those are the instruments that we would use to define information that is conveyed by these events. Probability is the instrument that we will use. We will not use relevance. Relevance, as we've discussed, is completely subjective. Okay. So Having said that, we now know that information of an event X is dependent on the probability of that event. So the information can therefore now be expressed as a function of the probability instead of a function of the event itself. Now let's get a little further into the problem statement. Okay, so the problem statement, the goal is to derive information as a reasonable function of P, the probability. Note that I've already replaced X with P. So in the previous slide, information was a function of X. Now I'm claiming that information is a function of P, of probability of X, which means the other attributes of the event X are completely out of the picture. So now we have to derive information as a reasonable function of P. Now what do I mean by a reasonable function? Note that this is not a real derivation. Okay? It's not as if somebody is asking to prove Fermat's last theorem. I mean, surely in the world, like maybe 5 people can do so. But the point is not that. The point is basically derive a reasonable expression for the information function. This is a quantity that needs to be defined. It is not a pre-existing quantity. We have to assign a function to I of P such that it satisfies our intuitions that this function needs to uphold. So let's get into that. So in order to derive information, the expression for information through intuition, let's walk through certain exercises. So let's look at the following 2 statements and let's try to figure out which of these 2 statements contains more information. The sun rose from east today, or that there was a supernova in the Milky Way galaxy. Okay, which of these events contains more information? Pause for a while and try to think about it. Now let's look at another pair of events. Okay, so Australia wins a gold medal in athletics and India wins a gold medal in athletics. Again, pause for a moment, think about it. Which of these statements truly contains more information? Now to answering this question, let's look at the first one. So which of these statements contains more information? Sun rose from the east today, or there was a supernova explosion in the Milky Way galaxy? Well, clearly, sun rises from the east every single day. Every single day you see that sun rises from the east. It has never been otherwise. The only way it can change is if it maybe some very massive object were to collide with the earth, change the spin altogether, but then we will all be dead anyway. So sun will always rise from the east unless, of course, something catastrophic happens. The probability of that happening is the probability of sun rising from the east is 1 practically. And whereas there was a supernova in the Milky Way galaxy, the probability is 2 less. It's very unlikely event. Because supernovas are pretty common, but supernova in Milky Way galaxy is what we are talking about. So how often do those happen? I don't know the real probability of it, but the point is that it's a very unlikely event. And therefore, if that event happens, we know something huge has happened, right? So we know a lot of information, okay? So the fact that an improbable event has happened means that we have gained a lot of information. So let's look at the other pair. Australia wins a gold medal in athletics and India wins a gold medal in athletics. So of course, India winning a gold medal will be a bigger news. I mean, just think of it from a national news perspective. Australia winning a gold medal, that might be a news item in one of the cities. Our city's local boy has won a gold medal in athletics or something. But in terms of national news, it will only be statistics. It will be, okay, we have won 58 gold medals, or we have won 80 gold medals, or something like that. In India, however, where gold medals are so rare, winning gold medals in Olympics especially is so rare, that if any of our athletes were to win a gold medal, that would be national news. and there will be like so much media coverage on that person's family, on that person's, like, who were the person's teachers, who were the person's friends, what sort of training he went through, and all of that. Probably we win like a gold medal every century or something. It's so rare that the information that would be conveyed by this event would be much more than if an Australian were to win a gold medal. So to summarize what we just said, information conveyed by a less likely event is more than the information conveyed by a more likely event, and that's a fact. Now let's look at how we can express this in terms of mathematical expressions. So we arrive at our first constraint, that information of an event with the probability P1 is greater than information of a event with the probability P2 if P1 is less than P2. I'm just simply mathematically translating the statement, the first statement that I made, into just mathematics. Now let's use these constraints to define information values for two special values of probability. Let's say the probability is 1. What is the information that we gain? Let's say we define that as 0. If an event is certain to happen, we actually don't gain any information whatsoever. And if the event is not at all possible, it's like impossible, then the information content in that event is infinite. In fact, this is like this is not a possibility, right? That an event with 0 probability can never happen. But let's look at it from a limits perspective. An event with an infinitesimally small probability, that event happening would have a very, very high value of the information expression. It would be of very informative value. So the information of 0 is infinite, or information of something that tends to 0 is very, very high. So these are the three constraints that we can think of, and of course B and C satisfy A very clearly. So that's good. Now let's look at, is that enough for us to basically come up with a function? Not yet. We have to do some more magic to figure out what that expression needs to be. But a small note here, information of P is defined over 0 less than P less than equal to 1. If the probability is, say, greater than 1, which is not even possible, you can never have a probability greater than 1, then of course the information expression itself will be undefined. So we will never even attempt to define information expression outside of the range 0 less than P less than equal to 1. Okay? And we always maintain that it is a positive real number. Well, assuming 0 is also a positive number, we'll say that's a positive real number. So let's build some more intuition into this. Let's try to build a little more intuition so that we can come up with an expression for information. Let's think about a composite event. Two mutually independent events that have both occurred. Okay, let's take an example. A pilot falls asleep flying the plane, and US President visits India. So these are two different events. They are no way related to each other. US President visiting India and a pilot flying a plane and then falling asleep within that plane. These are completely two independent events. Okay, and let's say that this composite event has happened. Let's say that when I say this composite event has happened, I mean that both of these individual constituent events have happened. So what is the way I can express the information of this composite event? It's simple. The information content of this composite event is the sum total of information content of its constituents events. As simple as that. Take a moment to think about it as to why this is true, but it's very logical. Yeah, so let's see how this translates in terms of mathematical expressions. So information of two events x1 and x2 both happening, which means x1 intersection x2, is information of x1 plus information of x2. Now we already know it's a mutually independent event, so therefore in terms of probabilities, probability of x1 and probability of x2 get multiplied. for the intersection, and that makes it information of probability 1 times probability 2 is equal to I times I of P1 plus I of P2. So this is a very important constraint that we have just derived, purely based on our intuitions. Okay. Now we'll take this constraint and move forward, okay, and try to come up with a mathematical definition. So you have a look at this expression and try to figure out where you have seen a similar expression. Have you seen something similar to this? I'm sure you have. If you have been through high school mathematics, you know what this is. It is the log function. So log of P1, P2 is log of P1 plus log of P2. Okay, as simple as that. Log of P1, P2 is log of P1 plus log of P2. There's nothing fancy here. So let's try to define information of P in terms of log of P. Let's say it is K times log of P. Okay. Now this is I'm choosing some K so that I don't lose generality. But the thing is, if you multiply both sides with K, the expression above remains true. Therefore, we'll say that information of P is K times log of P, where K is something yet to be defined. Yeah. Now let's try to apply this one to expressions A, B, and C, and let's see if it puts some constraints on the value of K itself. Now, in order to satisfy A and C expressions, we need K to be negative, whereas for B, either positive or negative values could work. Now, I'm not going back to what A, B, and C were. Those were very simple expressions. So for B, it was simply like I of 1 is equal to 0. Okay, information of a certain event is 0. Now for that to hold true, you can have K being any number. Okay, K can be any number, and it will be true because anything multiplied by 0, anything finite multiplied by 0 is 0. Whether it is positive or negative, that doesn't matter. But for satisfying A and C, what you would find out that you need K to be negative. So I of 0 should be infinite, right? Whereas log of 0 would be negative infinity. Okay. So therefore, you need K to be negative so that negative and negative signs cancel out, and you can get positive infinity. So you need K to be negative. That's the long story cut short. So you need K to be negative. Let's choose a value of K that is negative. So for simplicity, we'll choose K to be negative of 1. Okay, and as simple as that, we have an expression for information. Information conveyed by an event P is minus log P. As simple as that. Okay, let's get into the next slide. What is the base for this logarithm? We have defined it as minus log P, but what is the base? The fact is, it doesn't matter. All we would end up doing by choosing a different base is that we will get a different value of K effectively. It's basically a constant multiplying factor, and it doesn't matter. So therefore, we typically choose 2 and define the units as bits. So bits of information is what we care about, and when we choose a bit base as 2, we get the units as bits. So information of an event with probability P is minus log P to the base of 2. That's how we represent information conveyed by an event. As simple as that. That's the expression, that's the derivation. There is no real derivation in this case. It's just a derivation by trying to fit a function, trying to find a function that fits our intuitions. That's all that it is. Now let's look at some of the examples. So example 1, sun rose from the east today. Well, we knew that sun was going to rise from the east today, right? So the probability of that was 1 anyway, and the information content of that event is 0. Okay? There was a supernova explosion in the Milky Way galaxy. Okay, and let's say the probability of that happening was 10 to the power minus 15. Okay, I'm just making it up. So in that case, the information content of this event is just 49.83. well, not just 49.83, it's very, very, very high information value. So it's minus log 10 to the power minus 15 to the base of 2, and that comes out to be 49.83. So these are two specific examples of events that are very highly probable. This event is very highly probable, and this event has very low probability. So the event that has low probability definitely has a higher information value than the event that has high probability, or in this case, absolute certainty. Let's look at a more interesting example. Let's say that we are interested in only two possible event types. Okay, those two event types are that India may or may not win a gold medal in athletics. Okay, or there may or may not be a supernova explosion in the Milky Way galaxy. These are the only two kinds of events that we are interested in: India winning a gold medal or not, or a supernova explosion happening or not in the Milky Way galaxy. Okay, and let's say their respective probabilities are 10 to the power minus 5 and 10 to the power minus 15. Of course, these are just arbitrary numbers that I just picked out. Now the interesting thing is you are allowed to observe only a single event. You can only ask for whether India won the gold medal or not, or you can ask for whether there was a supernova explosion or not. You cannot ask for both. Okay, so which event should you ask for? Which event should you try to measure or observe? Okay, couple of notes. Well, first of all, this one we have not yet defined how do we mean by which event you should measure. What should we try to optimize? So of course the goal is to maximize the information that we are going to learn by observing this event. We want to maximize the information that we can learn. Having said that, it's a very important note, the actual outcome of the measurement is not yet known. We don't know yet whether India did or did not win the gold medal. We don't know yet whether the supernova explosion did or did not happen. We are only allowed to ask that question without knowing the answer, right? So we don't know. Of course, if supernova has happened, it's a lot of information, right? But it's also possible that the supernova didn't actually happen. So we have to take that into consideration. Okay. So let's see how we will be solving that. So let's first list down what is the information value of certain events respectively. Information of India winning a gold medal is 16.61. Information conveyed by India not winning the gold medal is 1.44 times 10 to the power of minus 5. These are simple application of the minus log p expression that we have already derived. Information conveyed by supernova happening is 49.83, and information conveyed by supernova not happening is 1.44 times 10 to the power of minus 15. Okay, as simple as that. Now out of all of these four, you can find that information conveyed by supernova is the highest. So if you already know that supernova has happened, we know that that's the most amount of information that we can get by observing any of these two possibilities. But the thing is, we don't know already whether supernova did happen or did not happen. We don't know yet already that gold medal was won by India or not. Okay, we only know what are their probabilities, and we only know the information conveyed by specific events. India winning a gold medal, India not winning a gold medal, supernova happening, supernova not happening. Okay, so what do we do next? It's not that complicated. We have to just maximize the expected amount of information that we are about to gain from the system. Okay, so we have to take weighted averages. So expected amount of information for gold medal. And by the way, look at the left and right expression. In the left expression, I have made G capitalized. So which means that gold here stands for the random variable that can have two values, gold with small g or not gold with again small g. So it can have these two values, gold and not gold. Okay, it's a Boolean random function. So the expected value of the information conveyed by that event is the weighted average of the information conveyed by gold and and not gold. And for taking that weighted average, we need to multiply them by the respective probabilities and take a summation. It's a very simple application of how we do expected averages. And that comes out to be 1.81 times 10 to the power of minus 4. Okay. Similarly, we look at the expected value conveyed by a supernova. Again, note that S here is capitalized. And that the expected value of that random function comes out to be 5.13 times 10 to the power of minus 14. So what it shows is actually that the expected value of random variable gold is higher than expected value of random variable supernova. Even though the information of supernova with a small s is higher than information of the gold with a small g, right? We know that supernova happening conveys much more information than India winning a gold medal. But on average, if we are to measure these events without knowing the actual outcomes, on average we will find that the expected that the information that we gain by observing whether India won a gold medal or not is more than the information that we can gain by observing whether supernova happened or not. Okay, so that's very important observation. Okay, observing whether India won a gold medal or not yields higher expected information despite being a more probable event. Okay, so you might think that this is violating one of our intuitions, that events with lower probabilities have higher information values. Well, that is not the case here. We are not measuring specific events. All we are doing is measuring the expected value of a random variable. Okay, and let's take another example, right? If you know that if you have two coins, you have a unbiased coin, okay, and you have a biased coin. So the biased coin will give you a head only once in 1,000 flips. Okay, so 999 times it will give you a tails, and one time it will give you a head on average in 1,000 flips. So which one of them gives you more information? Now the unbiased or the fair coin, you get a head, you get a tail, you absolutely don't know in advance. You absolutely don't know, it's completely random. Whereas the biased coin, you can pretty much say beforehand it's gonna be a tails. Okay, you can pretty much say beforehand that it's gonna be a tails. I already know it's gonna be a tails, because you know that it is more predictable, that it is more likely to flip a tail than flip a head, and much more likely in fact, and therefore much more predictable, and therefore a lot less random, and therefore on average you gain very less amount of information by flipping a biased coin, because more often than not it's going to be falling into the predictable bucket. So therefore the entropy of, well, I haven't yet come to the term entropy, but let's talk about the expected information communicated by a biased coin is less than the expected information conveyed by the unbiased fair coin. So entropy is measure of that randomness. Okay, so that's how we define entropy. Entropy, h of x, is nothing else but the expected value of I of capital X. It is a measure of amount of information gained when observing a random variable x. As simple as that. In terms of the mathematical expression, now let's derive that mathematical expression. We know that entropy is basically the weighted average of information of x, and therefore it is sigma of p of x times I of x over all possible volumes values of x within the random variable capital X. Okay, so in the set of variables that the random variable x can take. So therefore it comes out to be, now we already know this expression for I of x, we can substitute that here and we get an expression that says minus sigma p log p. Simple as that. That's how you get an definition and expression of entropy. Entropy is the measure of average amount of information that you gain when you observe a random variable x. So next time somebody tells you that this is the expression of entropy without giving you any intuition behind it, you already know that why entropy is defined the way it is defined. This is the way it is defined, and there is a reason for it, because it is the expected value of the information conveyed by a random variable x. Okay. Now let's move to the next topic, which is basically when does entropy get maximized, right? So we have already seen a couple of examples where we were talking about a biased coin versus an unbiased coin. The biased coin has lower entropy, has lower amount of information that it conveys on average. It is more predictable. The unbiased coin is more random, and therefore it has more information to convey based on a single outcome. But that's the intuitive part. But let's get to the mathematical part. Okay. So consider a Boolean random variable x, and it has the probability of its two states are p and 1 minus p. So what is its entropy equal to? We just substitute the values p and 1 minus p into the expression for entropy, and this is what it is, right? As simple as that. Now the goal is to maximize this entropy function, and to do that, we are going to take a derivative of this expression with respect to p, and this is what we get. Don't worry, you can figure out the derivative. It's very simple. It comes out to be log of 1 minus p minus log of p. As simple as that. And because we're going to maximize it, so the first derivative needs to be 0. So substituting the first derivative equal to 0, we get log p equals log of 1 minus p. And so basically this applying the anti-log now gives us p equals 1 minus p, or p equals 0.5, which means at p equals 0.5 the first order derivative vanishes to 0, and that's a point where we can have the maxima, minima, or inflection. Let's not go into the more details of that, but suffice it to say that entropy gets maximized at that point. So the entropy for a Boolean random variable is maximized if both outcomes are equally likely, that both outcomes have a probability of 0.5. And this can in fact be generalized. If we were to generalize this, then the statement holds true irrespective of the number of outcomes possible. Basically, the entropy of a random variable is maximized if all possible outcomes are equally likely. And that makes sense also, because you see, let's again go back to our intuitions, and you have 3 events, one with a probability of 0.99, the other two with say probabilities of 0.005 and 0.005. You know more often than not that the event with a probability of 0.99 is what's going to happen, and therefore the information that you gain based on the outcome is in fact most of the times it's very, very low. So therefore the entropy is maximized when there is a uniform distribution, when the probability is equally likely for all the possible outcomes. Moving on to the conclusion. So in order to conclude, we can say that information theory has a wide range of application, be it linguistics, NLP, cryptography, pattern detection, etc., etc. It's used in networking, error control mechanisms, stuff of that sort. In case of the classification problem in supervised learning paradigm, in the decision trees, it's used to figure out what is the best possible decision tree. It's you can apply information theory concepts to the English language itself, and you can find that the entropy of English language of single bit of a single character of English language is not very high. There is a lot of redundancy in the English language, and that's useful because the way the brains work is that they read word by word. They don't read character by character. And there are chances of errors happening either in terms of the mind misreading a particular character, or in terms of printing of a particular character, in terms of typing it, etc. And the fact that English has so many redundancies helps basically make sure that despite those redundancies, despite any errors, the understanding is correct. So that is one application of information theory. So there can be many, and in fact, all of those applications require a solid understanding of the concepts of what is meant by information, how do we measure it, what is meant by entropy, and how it is measured. And I hope that this lecture has been an occasion where many of your misconceptions might have been clarified. These concepts have now become solidified. So I hope this was a useful lecture.